Hello everyone, I'm Prashant and I'll be presenting my work GLiDR, Topologically Regularized Graph Generative Networks for Sparse LiDAR clouds. This work was done at IIT Delhi with students from IIT Indore as well as BITS Pilani. So let's dive in. Sparse point clouds are low cost, faster computation, but they have poor navigation, whereas dense point clouds have higher cost, slower computation, but they give good navigation. There are several challenges with sparse LiDARs. Existing generative models fail with sparse LiDAR data, as well as segmentation is challenging, even with static reconstructions in label-free settings. Reason is that there are few points that are falling on dynamic objects, as well as low density of points per dynamic object. Here we see that existing methods fail miserably with dynamic to static transition for sparse LiDAR clouds. This is the input dynamic scan. This is the expected static output, and this is the best baseline static generation. So this totally is not able to capture any walls or long range dependencies, and it's not able to capture the topology of the LiDAR structure for a sparse LiDAR. So why do existing generative models fail with sparse LiDAR? One of the major reasons is that they fail to maintain long-range dependencies and the global topology, and fail to maintain global structures because they cannot capture the global topology like walls, fences. So here we show a small example. This is a ground truth static LiDAR. This is a dynamic LiDAR, and this is given to the best baseline model. So this example is for a very high density LiDAR. We just see that even if it's given, even if the best baseline model gets best baseline model with the state of the art gets high density LiDAR, even though it reconstructs the local structures, it fails at the global structures. This is a big problem. This is a big problem with this is a big problem because the local structures cannot be maintained, while the ground static LiDAR has very accurate the global structures cannot be maintained in the output reconstruction, while the ground truth static has very accurate global structures, as seen by these red regions. In the reconstructions of the baseline SOTA model, the ground truth static long range dependencies are not met because the model cannot capture the global topology. So the proposal is, can we transform a sparse dynamic LiDAR scan such that it provides the benefits of a sparse as well as a dense LiDAR static scan? So what I mean is, can it be low cost, faster computation, as well as better navigation? So there's an intriguing observation that we see is that despite sparsity, global LiDAR topology may remain intact and can be inferred using certain topological methods. For instance, if we see a sparse LiDAR here, we're able to infer the global topology of this scan using topological data analysis methods. So this is what we're trying to use. So our solution is a dynamic graph generative method with topological priors that can help us get all the three benefits in a sparse LiDAR. So the solution is we visualize LiDAR as a weighted graph where the nodes represent the features of a 3D point and the edges represent the closeness between these nodes. The goal is to learn features between closest k LiDAR points recursively. This helps us to learn local neighborhood information as well as the recursive stacking of these help us learn the global shape properties. These long-range structures can form a strongly connected cluster, and as such, long-range structures can be easily formed. Now we'll show just an example of the graph generator neighbor. Let's assume that this is a LiDAR, which is a point cloud. We create a graph out of this point cloud by using k nearest neighborhood, and the distance at the edge weight denotes the distance between the neighborhoods. So here the x is the xi is the node and xj are the neighbors. And then we do edge convolution as proposed in dynamic DGCNN, dynamic graph learning on point clouds, to update the central node based on the closeness of the other nodes. And we use edge convolution to update these features. Now, after this, we destroy the, after updating these features, we destroy the graph at the current, we destroy the graph at this current stage. We destroy the graph at this current stage and reconstitute a new, reconstitute a new graph, reconstitute a new graph. We reconstitute a new graph using the updated node embeddings. These node embeddings are updated previously according to the closest neighbors, and now a new graph will be created using the new embeddings. So now we'll deal with topological pairs, and I'll explain how what topological pairs help us with. So existing deep learning methods cannot ensure global geometry, but only local geometry. And existing methods cannot ensure the local geometry, and they can only ensure the local geometry. However, topological priors can help us enforce global as well as local shape, because topological priors can extend to larger distances, as we saw in a backbone structure. So what we'll be doing is we'll be dealing with simplicial complex, which are used to represent topological spaces. For instance, you see graphs. This is simplicial complex. This is 0, 1, 2, 3 simplicial, and this is a clique complex, and this is a cycle, and these are cycles in simplicial complexes. We use simplicial complexes to represent topological structures. So simplicial complexes are used to represent topological spaces. We can generate these simplicial complexes using filtrations via alpha neighborhood balls at different spatial resolutions. For instance, you see that this is a point cloud, and we use a filtration by generating alpha neighborhood balls, and these alpha neighborhood balls, after certain spatial resolutions, increase to give the global topology that is a circle for this particular point cloud. So our goal is to preserve the global topology of LiDAR using zero-dimensional persistent homology, which the zero-dimensional persistent homology denotes the connected components that are created in a point cloud. So we constrain the point generation, point augmentation of a sparse LiDAR scan along this global LiDAR topology, so that we have new points that belong to static structures that can help in better navigation as well as accurate segmentation, which is in general not possible with sparse LiDAR. So these things help us preserve these augmentations when done across the global topology, help preserve global structures as well as augment new points along the global topology, which increases the density along the global static structures. So zero-dimensional persistent homology-based backbone is a backbone where, assuming we have this original LiDAR, and then using filtrations, we get to a certain backbone, and at the end of this filtration, we have a single zero-dimensional persistent homology, which is a single connected component, which is the backbone of the LiDAR. So the left denotes the global topology of a LiDAR scan. This can be easily added as a regularization constraint to a model. The model will then follow the skeleton while generating and augmenting static points to the sparse LiDAR scan, and it will augment those static points along the global static structures. This helps to preserve the long-range global. Structures. This helps to preserve the global long-range structures. And also, for instance, this is the global. So let's say while training at the start epoch, this is a global LiDAR scan. This is a LiDAR scan. Well, after some training, we get certain disconnected components. While we continue to do the filtration process and train the model with this homological topological prior, we see that at the end of the training, we find a global topology that is a zero-dimensional persistent homology, which is in the form of a connected component. At the initial state, we have certain point clouds, and as the filtration starts, you get certain edges and some disconnected components. These disconnected components move across and they become more higher, they become more, they increase in size, as well as they increase in the size, as well as the size increase because of the filtration size increasing, because of the alpha neighborhood bonds that increase. And at the end, we get a single connected components where all the components merge into a single connected component. This is where this this is the death of these connected component, where this is the birth of the connected component. So our main aim is to ensure that the first connected component that is created only persists at the end, and all the other disconnected components that are created are merged in only one connected component. So what we do is we create a topological loss that tries to reduce the persistence of all components from the second component to the nth component, and only increase it, but it does not reduce the persistence of the first connected component. So the first connected component, by this, ensures that all at the end of the filtration, all the disconnected components merge into a single connected component. This is what this particular loss ensures. This is from I is equal to 2. That is why it's from I is equal to 2 to n. So I'll just explain the model now. Given a dynamic LiDAR scan, we pass it through a graph layer, which consists of, where we create k-nearest neighborhood, we do a graph edge convolution and a max pool. And this is the final layer. We then apply the topology constraints on the hidden representation at the second and the fourth layer, which gives the zero-dimensional persistent homology constraint. This constraint is developed based on the topological laws of the birth and death pairs from the second component to the last disconnected component that was created. Now we pass this in point cloud through the decoder that helps to project back the high dimensional LiDAR point embeddings to the three-dimensional point cloud, and we get an augmented LiDAR. Now we also do a filtration on this to obtain the persistent homology constraint on this particular LiDAR scan. We also do take a point-to-point correspondence score and a loss between the static corresponding static dynamic LiDAR, corresponding static LiDAR for this dynamic LiDAR, and we do a point-to-point correspondence and take a loss that tells the discrepancy between the static LiDAR and the dynamic LiDAR. 5:15 to 6:45, session 4 at Exhibit Hall R4AE. You can also mail me for any clarifications issues that you require. Thank you.